Hi, I'm Paul Mason, and I'd like to speak a bit about tides. And tides are nothing more, nothing less than gravity at work. We can see from this illustration how the moon causes the tides on the earth, and we see that this pole here marks a particular location on Earth, and as that position in the center of Earth and that position in the moon all line up, then you're going to get the highest tide. Now they're no longer lined up, it's now 90 degrees, it's a low tide, and then when we go to here we get high tide again. So the position is still lined up with the center of the Earth and the moon, except on the other side. So here we have the observer is between the center of the Earth and moon, that's high tide. When it's at a 90-degree angle, that's low tide. And when the moon is in the opposite direction, that's high tide again. So we have high tide approximately twice a day, and we can see that it's not exactly twice a day, and this is because the Earth is spinning and the moon is orbiting the Earth at the same time. Now the reason why this works is that the water on the side of the Earth closest to the moon, it feels a stronger pull of gravity than does the center of the Earth. So the water will rise up. And then when it moves to another angle, it can lower down. And this we can see high tide here and low tide at this particular location shows an extreme situation between high tide and low tide. Now in this animation we also see, of course, a big exaggeration, but the fact that the moon is pulling on the oceans, this works on the crust of the Earth as well, pulling it toward it, so as the Earth is spinning and the moon is going around the Earth, we see this tidal bulge always pointing toward the moon. But we see a similar, very similar tidal bulge on the opposite side. So even though the moon is on this side, you're getting high tide on the opposite side of the Earth at the same time. So this is gravity at work producing tides on the Earth, but both the sun and the moon generate tides, but the moon's tide is twice as strong as the sun, but combined they have the strongest. So when the moon is here, which from Earth this is a new moon, we see that we have very strong tides, and this is called a spring tide occurring at new moon. When we have the moon in this position at a 90-degree angle, the moon is producing a high tide, but the sun is producing a high tide at a 90-degree angle, so the moon and sun tides are canceling out, and so the tides we get at this time of the month are going to be weaker, and we call those neap tides. Spring tide again, when Earth, moon, and the sun all line up, this would be the full moon, so we have the highest tides at full moon and at new moon, and this is again called the spring tide. Nothing to do with the season, but thinking of the springing up of the tide. The neap tide is the canceling again of the strong moon tide and the weaker sun tide. So you still get high and low tides based on the moon, but they're not as high and not as low as they are during the spring tides. So the tidal effects that I've just described are on the water and crust of the Earth. A mountain, for instance, will also rise and lower due to the tides, but only an inch or so every tide. So that's a very small effect. And this is a weak tidal effect because we can think of it as the Earth as being a large object being affected by a smaller object, the moon. Now, if we have tides in which the reverse is true, where you have a large object affecting a smaller one, then the tidal effects are stronger and we have different effects that we can see. For instance, there's a resonance between Mercury's spin and its orbit. So Mercury spins 3 times for every twice it orbits the sun. For every 2 times it orbits the sun, it spins 3 times. This is because it's close to the sun. It has a strong tidal effect from the sun. And the tidal effect is pulling one side of the planet more strongly than the other side. The front side is being pulled more strongly than the back side. And also Mercury has an elliptical orbit, a pretty elliptical orbit, which means it's not a one-to-one synchronization. The moon, for instance, it spins exactly the same rate as it orbits the Earth. So because the moon receives a very strong tidal effect from the Earth is pulling on the near side of the moon stronger than the far side, and that keeps it locked so that it spins 1 time for every orbit around the Earth. Jupiter's moons, Io, Europa, and Ganymede, all have a resonance, and this is a different kind of resonance. It's not spin-orbit. These are the orbits all locking together. And so for every 1 time Ganymede orbits around Jupiter, for every 1 time it orbits around Jupiter, we see Europa orbits twice and Io orbits 4 times. So Ganymede is coming around for its first full orbit, and Europa has orbited twice and Io 4 times. So this is because of the strong tidal forces of Jupiter on the different moons, and as well the interactions between the moons pulling on each other, which causes these resonances. Callisto is not really affected. It's about twice again far away from Jupiter as Ganymede, and it's only very weakly affected by tides. We also have geophysical effects. These are for very strong tides on for instance, the closest moons, large moons to Jupiter, Io and Europa. Volcanoes exist on Io due to the fact that you have a very large planet, Jupiter, pulling and tugging by the tidal effect on Io. It's pulling on one side stronger than the other side. That's kind of like taking a fork, say, and pulling it and bending it back and forth, and then in that process you heat it. And Io has been heated by being pulled back and forth by Jupiter and being tugged on by the moons as well. And it's caused the interior to be liquefied, molten, and we have volcanoes on the surface of Io as a result. On Europa and Ganymede, probably not on Callisto, but we're not completely sure, but those tidal effects can cause subsurface oceans where the surface has a layer of ice, but below that it is a ocean, and that's because of heat from inside generated by these tidal effects. So if we look at those effects, those effects are prominent literally on the surface of these objects. As we move from close to Jupiter to far out, So don't concentrate on the sizes of the objects, but let's concentrate on what's on the surface. So on Io, we have all of these colors from different compounds of sulfur, and we have volcanoes actively spewing lava, lots of dark areas in different colors. Very few craters. All the craters have been filled in with lava. Moving further out, Europa, less tidal effects. However, the entire surface has been frozen and melted and refrozen over and over again. There are very few craters on the surface. It's been very smooth over because of that refreezing. Ganymede. It has lots of craters, indicating that there hasn't been much change in the surface features, but some areas are smooth and have very few craters. The lighter areas, the darker areas have many more craters. And so it's kind of in between. It is getting strong tidal effects from Jupiter, but they're not strong enough to resurface the whole moon, just certain areas. Then Callisto. Callisto, the entire object looks a lot like the dark areas on Ganymede. Very highly cratered. Callisto has more craters than any, more crater density than practically any object in the solar system. And it is virtually unaffected by the tides. So the differences between all of these objects, it's a very different, a very large range of properties, but the range of properties has to do with the strength of the tidal effects of Jupiter. And so that is tides, gravity at work.